some of you might remember a little shortcut from last year. On your graphing calculator, you could go y equals x squared, y equals x cubed. Go to your table, second graph. Boom, they're right there. So if you go to y equals, type in x squared and x cubed, y1 x squared, y2 x cubed, and then second graph, there's your tables. Did anyone learn that last year? Some of you know, some of you yes. Okay, so we did y1 equals x squared, y2 equals x cubed, and then second graph, and that'll show you this exact same table. Okay, especially your perfect squares, those should not have been an issue. If they are an issue, then it's time to pull out the tissue. And then the flashcards. I should have been a rapper. No? Okay, 3 cubed is 27. 4 cubed, 64. 5 cubed. Yeah, so memorize at least up to 5 cubed, please. 6 cubed, 216, 343. And we have 512. 512, if you're into computers and programming, 512 might sound familiar. Sort of gigabytes and stuff. Binary, no? Okay. 7 cubed is 720, or 9 cubed, sorry, 729. Everyone's favorite, 10 cubed, 1,000. There is a little pattern for 11 squared, 11 cubed. It doesn't hold after, like it works for those two. I'm pretty sure 11 to the power of 4 doesn't look as nice. Oh, it does. 1, 4, 6, 4, 1, but after that, it's not anything special. Okay, and 12 cubed is 1728. So let's do a little bit of review. Okay, the little number, and it is very important that you write your radicals properly, especially as an AP student. Notation is really important. And when you get to your AP exam, that is going to be important if you write things properly and your notations properly, right? So your index goes inside the little, I don't know, I tried to make an analogy there, but I don't know if it works. The little V goes in the V, I don't know. The index. If it's a 2, we don't have to write it, right? Square root of 2. So I think I have written that here, highlighter. I square root, and it's 2. We don't really write the 2. That is 2. We don't write the index. If there is no number, then it's square root. That's all saying the same thing. R is the coefficient, X is the radicand, so everything underneath the square root is the radicand. And our squared symbol, the radical symbol, right? So that's review. Do you remember that? Yes? Maybe not? Let's try and... I wrote down our radical properties. This one got weird for some reason. Sorry. And we're going to cover this. We're going to cover these in depth over the next couple days. Let's talk about converting. If we want to convert an entire to a mixed radical, okay? So this is for square roots. We can adjust it for cube roots or fourth roots. One is we find the largest perfect square that you can divide the radicand by, or basically the largest perfect square that's a factor of the radicand. So in layman's terms, find the largest perfect square that you can divide the radicand by. then we write it as a product. With that perfect square and whatever number makes the original radicand. And last, we're going to actually root the perfect square. So that's me trying to write it as layman terms as possible. Root the perfect square. So for example, let's do this right below. If we had square root of 32, okay, now you could make a factor tree, or we can use that chart that we have and find the largest perfect square that will go into 32. So usually we work our way backwards. So if we look at our chart, our table, 36 is larger. Will 25 just logically go into 32? No. So 16, will 16 go into 32? Going backwards up the chart. We're going up this way. Will 16 go into 32? So we check how many times? Twice. 4 would also go into 32, but we want the largest perfect square. So 16 times 2. Okay. And the rules above, I already wrote it down. We could also, instead of writing this as square root of 16 times 2, how else could you write this? Square root of 16 times square root of 2. Yeah, root a times b equals root a times root b. And then last, we actually square root the perfect square. What is a square root of 16? 4. 4 root 2. Okay? Please make sure that your equality statements, everything is actually equal to what is written before. Okay, I'm going to start getting stricter on that. All right, turn the page. Whole bunch here to try. Let's go through the first two and then you try C and D. So root 75, I gave the answer there. Oh, it needs to be larger. What's the largest perfect square that goes into 75? 25 times 3. Here is when your multiplication tables, knowing them, really helps you. I mean, it always helps you, but man, in radicals, it makes you so much stronger and faster. What is the square root of 25? 5. 5 root 3. Okay, 80. 4 will go into 80. Is there a larger perfect square that goes into 80? 16? Check. Does 16 go into 80? Yeah, how many times? 5. So we can write 16 times 5, or root 16 times root 5. And then we actually square root the perfect square. Does this look familiar? Yes, hopefully. If not, time to get familiar again, I guess. 4 root 5. All right, you try C and D. Easy. Peasy, lemon squeezy. I'm sorry. I apologize. You done? Yeah. 8. What's the largest perfect square that goes into 8? We can write it as root 4 times root 2. What's the square root of 4? 2. Good. Hey, do you remember how to check your work? Come on. Are these real numbers? Are they real numbers? Oh, come on. What type of real numbers are they? Irrational. Yes, they are real numbers, the irrational. Everything you could type in your calculator is a real number, right? Your calculator handles the real number system. So these are real numbers, therefore we can type them in. Can you type in root 8? Yes. And then type in 2 root 2. Should they be the exact same thing? Yeah, they're the same decimal. We never want to write decimals. Okay, we want to write things as an exact value, especially in 20 and 30, because decimals are ugly, right? What happens if you try, what happens is students start to round and then they keep rounding too early and they round before their final answer and it compromises the solution. By keeping things as an exact, it's neater and it also is more accurate, more likely to be accurate. It is actually more accurate. It's exact as opposed to rounded, right? Okay, so you can check your work. What'd you get for 20? 2 root 5, because root 4 times root 5, and we actually square root the perfect square. So we can only square root 4. We cannot square root 5 without it turning into a decimal. Okay, we only want natural integers, I guess. It's a cubic root. Okay, what about e? Is e fully simplified? It has a coefficient, but it's not fully simplified. I don't know if you can read that. Uh-oh. Not fully simplified. Oh, it's like way up there. Let me see if I can move it. I feel like the ground vibrates. Yeah, right? Weird. Okay, not fully simplified. Why? Why is this not fully simplified?
54 isn't prime.
54 isn't prime. Well, okay, that's one way to describe it. Yeah. What else? Not just that it's not prime, because root 6, for example, is fully simplified. It's not prime, but it's fully simplified. So specifically, what is divisible by 54? Is there a perfect square? 9. So it's divisible by a perfect square, therefore it's not fully simplified. Okay, so 9 times what? 9 times 6. Good. Now, this is where students really have it, they struggle with this. But you shouldn't struggle. It'll be okay. Just ask yourself, what operation is happening between these 3 different numbers? It's all multiplication. So when we take the square root of 9, is it still multiplication? Yeah, it becomes 2 times, the square root of 9 is 3 root 6, or 6 root 6. We're good? Any questions? Okay. So try F. Nine times 5. So it'd be, what's the square root of 9? What's the square root of 9? It's a 3. So it becomes negative 15 root 5. You can check your work, type them both in. Should be the same thing. Oh, it looks like I put a 3 beside it. Okay, so that was just 3. So 5 times 3, or negative 5 times 3 is negative 15. All right, this little fraction here, beautiful. I should have left more room. I'm sorry. Next time. This is the first draft of these notes, so I apologize. Not that I should make excuses, but I just did. Okay, so we can actually split this up as root 20 over root 49. Just like we have root a times root b equals root a times b, also square root of a over b is equal to root a over root b. Where can we go from there? Okay, simplify what? Root 49. What is root 49? 7. What happens if we have 7 times root 20 over 7? They cancel out, or they reduce to 1 actually is what's happening. 7 over 7 is equivalent to 1. So they reduce to 1. So we just have root 20, and what does that equal to? Root, a perfect square goes in 20. 4 times 5, or 2 root 5. Thanks for being champs. Sorry about that lack of room there. 2 root 5. The next one's nice. The 7th root of m to the power 7. M. They're opposite operations, right? Just like the square root of x squared is just x. Remember that the 7th root is the same thing as 1 to the power, x to the power of 1 over 7. Do you remember that? Oh, you can hardly read it. Let's do this. Do you remember this? Huh? Power over root? Right? This is the exponent, the power. I always call it power over root because I think of it as like when I teach my grade 10s, the flower power is over the roots. Do you remember Mario? Yeah, flower power. Right, okay, I say it wrong every time. Mario. Sorry. Okay. So in the last one, we had m to the power of 7 all to the root of 7. So that's the same thing as m to the power of 7 all to the power of 1 over 7. And 7 times the 7th is just 1. That's another way to think of it. No? Yeah. Those exponent laws, I know you loved them last year. Okay, the last one, I'm running out of room, so I'm going to maybe, so this, guys, really important. 63. Do you remember doing those in AP last year? Some of you? Some of you, it's going to be brand new, so I'm going to write on the next page, actually. So 63n to the 7th, square root. 63n to the 7th, and what was it? And then p to the power of 4. Thank you. Okay. So we want to break it up into our perfect squares and non-perfect squares. We want to make it a product. So let's start with 63. 63, what's a perfect square that goes into 63? 9, so 9 times 7. Okay, now n to the power of 7. So you can, think about it this way, we have 7 n's. 1, 2, 3, 4, 5, 6, 7. And when we take a square root, right, if we took the square root of n squared, what does that equal? N. So we want to be in groups of 2. Right? So the largest number of groups of 2 I can pull out would be 6 of the n's. Or n squared 3 times. Oh, this is such a hard concept to explain. So you have n to the 6 and n because we want the largest number of pairs that we can pull out. So if I did, let's say we split it up instead as to 4 and 3, well, that's not fully simplified because I can pull an n squared out of that, right? You could still square root of n squared. So you're always going to have, if it's an odd number with a square root, 1 left over. So 6 and 1. Okay, how about the p's? Can you square root p to the 4? Can we square root p to the 4? It's even, yeah. So it's actually going to go with our 9. It's a perfect square. P to the 4 is a perfect square. So that gives us, what's the square root of 9? 3. What's the square root of n to the 6? It's divided by 2. N cubed, you're dividing it by your index. The reason why is, remember, your index can be written as a fractional exponent. So if you're timesing by a fraction, it's like dividing by that number. P to the 2, and then square root of 7n is left over. You can't square root 7, you can't square root n. Should we try another one like that? Or go on? Do you remember those? I know the AP students in grade 10 always struggle with them. So I know it's probably been a while since you've seen that. And it's like, what? Let's go on and then we'll come back to a couple more examples if we have time, okay? Sound okay? Sort of get it? All right, converting mixed to entire is so much easier. So in layman's terms, raise the coefficient to the power of the index, or exponent of the index. To bring it inside the radical. Simplified. Actually, just leave that. Don't write that. Okay, so if I want to bring the 2 inside the square root of 6, are you all done writing? I'll wait a second. Raise the coefficient to the power of the index to bring it inside the radical. So if I want to bring 2 inside, what's the index? It's a 2. So it becomes root 4 times 6, which is square root of 24. It's 2 squared times 6. B would be root 81 times root 10, right? 9 is the same thing as root 81. They're the exact same thing, just written different ways. You can represent 9 so many different ways. One way is square root of 81, which is equivalent to what? Square root of 810. Can you bring a negative inside a square root? No. Cube root? Sure. Square root? No. Be non-real. So we're going to leave the negative outside. Just bring the 4 in. So what do we do to 4? Square it. 4 squared is 16 times 5 is 80. Negative root 80. Okay, bringing 15 inside a square root. What's 15 squared? 225. So just 225. I don't know it's written this way. This is 9 root 21. Okay, why don't you try that one by yourself? Right as an entire. So quickly on your calculator, go straight to taking your coefficient, squaring it, times the radicand. How would you bring 3 over 2 in? What's 3 over 2 squared? Okay, or as a fraction? 9 over 4. Square both numbers. 9 over 4 times 8. What is that? 18. Good. The 8 over 4 can actually reduce to 2. 2 times 9, 18. Try the next one. This time it's a cubic root. So cube it. So if you're cubing it, you're going to put in brackets in your calculator. But you should be able to cube one half in your head. Right? Just cube each coefficient. Cube the 1, cube the 2. You don't need to type that in your calculator. I mean, you can. 1 over 2 cubed times 80 is 10. Why? Well, 1 over 2 cubed is what? Hey. It's 1 over 8 times 80, or 1/8 of 80 is 10. Okay, how do we bring a to the 4 inside the square root? What would it be equivalent to? A to that, we double it, yeah. A to the 8. Because if you square it, we're really squaring it, actually. We're doubling our exponent because we're squaring it. When you square exponents, what's the power law? Power to power, we multiply it. Good. And so now, Same base being multiplied, what do we do with our exponents? Good old exponent laws. You can hide. They will find you. I know Halloween's over, but they're everywhere. Why? Because it's part of the real number system. Can't get away from it. It's like trying to hide from the number 2. You can't. Okay. Do you want to try the last one on your own? Yeah. Challenge yourself. It's Monday. I know. Is it on or off? True or false?
You can hide from 2 in minor.
You can't hide from 2. Yeah.
Just win. I'm just
Okay, so remember to bring it inside. Raise it to the power of the index. So one way to write this, so you're being very careful, you're raising 2 and k squared to the power of 3. Both of them to the power of 3. Right? This is equivalent to this, because the cubic root cubed, they cancel each other out. What do we get? What's inside this first bracket? Is it 2k to the 6th? No. What is it? 8k to the 6. Now, what is our solution then? If we're multiplying these two, 32k to the 7. Yay, good job. You got that? Nice work. So much easier, hey, to convert from an mix to an entire. Because you don't have to like find a number, you just do it. So much easier. Okay, let's get into adding, subtracting. So normally we'd have done a lot of this stuff tomorrow, but we are going to an assembly. So whatever class time we do have will be work time, the rest will be the assembly. Okay? So let's go on. Adding and subtracting radicals. If you have, so layman's terms again, the same radicand. You have to know what a radicand is. What is a radicand? You have the same radicand. The thing inside, usually the thing, like an expression, sure, expression or a number underneath the square root symbol or the radical symbol, right? This is your radicand. If you have the same radicand, you can add or subtract the numerical coefficients. And then simplify. Sometimes you have to simplify first, actually. Simplify if necessary. Necessary is 2c, right? 2 C's, 2 S's? 1c? 1c. Thank you. I know. Necessary is one of those words that just likes to...
I guess it isn't necessary.
I guess it isn't, because I've gotten this far without spelling it right. Okay, necessary prior to combining. All right. Simplify if necessary prior to combining. Good times. Remember, I don't know if you covered this last year. If not, this will be new. So think of it this way. Root 4 plus root 3, is that root 7? Well, what is square root of 4? Tell me. 2. What is the square root of 3 to, let's say, 6 decimal places? 1.7 32051. Okay? What is the square root of 7? Is it 3.7? No. 2.645751. So are those equal? No, those are not equal. So one way we like to talk about adding or subtracting radicals, it's like adding or subtracting like terms. You can only add an x with an x or a y with a y. They have to be like terms. Only with x squareds with x squareds. So only cubic roots with cubic roots. And square roots with square roots. So if we turn the page, oh, that's not what your range is. We are really thinking of it in terms of like x. If we know 2 plus 2 plus 2 is 3 root 2s, or x plus x plus x is 3 x's, then root 2 plus root 2 root 2, let me try this again, root 2 plus root 2 plus root 2 would be 3 root 2s. How many root 2s do we have? We have to have the exact same radicand to add. So, very basic example, let's look at the very first. If I have 3 root 5s and I want to take away 7 root 5s, how many root 5s do I have? So we subtract the coefficients, 3 minus 7, negative 4 root 5s. How could you check your work? Calculator. Calculators are tools to check your work or solve complicated problems. That's what they're there for, okay? They're not there to be a crutch, but they are there to help you. So 3 root 5 minus 7 root 5, and then negative 4 root 5, they should give me the exact same decimal, and they do. Okay? So it's true. So right now, can we subtract number 2? Do they have the same radicand? No. Let's see if we can simplify then. What can you simplify in root 4c? It's a product of 4 times c. I'm hearing it, whispers. 2 square root c. Can you actually square root 4? Yeah, it's 2. So we can write that as 2 root c minus, what can we simplify in the second one? 4 times 3, the square root of 9, times root c, which gives you 2 root c minus, how many root c's there? 12. We multiply the two coefficients. And then our final answer, how many root c's? Negative 10 root c's. Careful of the sign. That's a little bit a challenging one. 3 is a little bit nicer, kinder. So first of all, is looking at these radicands, can you simplify 11 or 5? Is there a perfect square that will go into 11 or 5? No, they are prime, so for sure, no. So we only add and subtract like terms. So root 11s with root 11s, root 5s with root 5s. Brings you back to grade 9 polynomials, hey? Those are simpler times. Yes. Okay, let's do the root 11. 6 minus 8. Negative 2 root 11. Negative 2 minus 3. Negative 5 root 5. Good. We add 4. Not yet. So if they're not the same radicand, what do we do? Simplify. Can you simplify 8? What perfect square will go into 8? 4, so 4 times 2. So what would that equal to? Square root of 4 is 2, 2 root 2, plus 18. Is there a perfect square that goes into 18? Yeah, which one? We can write it as 9 times 2. So what would that equal? 3 root 2, which equals how many root 2's? 5. Okay, try 5 and 6 all by yourself. Or with your neighbor. Okay, I'll write the solutions up on the board. So 5 would have been negative 6 root 5. you might get to a point, and I'm totally good with that, with going straight to the simplified form. You can do it in your head. If you do that, though, you have to really trust your mental math. Okay? So we should have had 4 root 3 plus 5 root 2 minus 5 root 3 minus 24 root 2. And so the final answer you should get, doesn't matter the order, so how many, negative 1 root 3 or negative root 3 minus 19 root 2. Yeah, you can write the negative 1. It's not needed, but you can. And then the last one, okay, we can break that into 4 times 5x minus, and this could be 9 times 5x. So square root of 4 is 2 root 5x minus square root of 9 is 3. 3 times 3 is 9. So you should have had negative 7 root 5x. Good? Adding and subtracting is pretty fun. I like adding and subtracting. Radicals. I'm not going to go through this stuff. We're just going to move on to the next page. I don't even know if we need to really cover the next page because we've already simplified. The only thing I could say is let's look at 4 and 5 really quickly again. Okay, so number 4, this is a 4th root. A 4th root. How would we break this C up? So you could do 2 and 7. We could do 6 and 3. How would we split it up if we want to fully simplify this? 8 and 1. So you want the largest, basically multiple of 4 that we can take out of the 9, right? There's multiple 4 would be 8. 4 and another 4 is 8. And then how many left over? Just 1. C to the 1. Does that make sense? Like this, with this, multiply is the same thing. Yeah, 8 plus 1. Remember, we add exponents when the bases are the same, and we're multiplying. 8 plus 1. If you did 4 and 6, you could still pull out another c to the 4. So it wouldn't be fully simplified. We really want the largest multiple of 4, which is 8. And then 1 left over. So what does that equal? What's the 4th root of c to the 8? C squared. One way to think of it is, remember when we did when we changed this to exponential form, it's power over root, 8 divided by 4, which is just 2. If you could actually change this to 8 over 4 if we want to change it to exponential form, which is how we get 2. Okay, try 48. Root 48 y to the 5. Simplify that one, and then we'll call it a day for the lesson. Okay? No, well, basically, tomorrow's the assembly, so whatever I'll sign today's and tomorrow's stuff, then if we have time tomorrow, we can do that. Okay, I'm just going to pause this. Found the error of my ways. Woo! That was a close call. Yeah, of course you're confused. That 4th root does not go away. That's better. Thank you. That was a close call there. Whew. Thank you. See those sneaky little indexes, especially when it's not a square root, right? So easy to forget them. Just because they're so little. What's the largest perfect square that goes into 48? 16 times 3. Okay. How are we going to break up y to the 5th? Y to the 4 is the largest, yeah, and then y, so that we can actually, y to the 4 is a perfect square. And that you should have 4y squared root 3y. Wunderbar. Okay, so your assignment for today and tomorrow. So remember that if we have class time tomorrow, it'll be work time. Is right here. You have it at the very front. I don't even have to write it down. Okay? So the assignment would be, okay, these two right here. Both of those. Okay? Radicals, so this is just simplifying radicals and then adding and subtracting some wonderful radicals. Easy stuff. Okay? So let's get your stuff out. We actually have tons of time, so it works out great. We've been lucky so far.